Go! Good evening at the third and final evening of Pint of Stavanger, Norway. Pint of Science, Stavanger, Norway. We're really pleased to be here, and I hope you enjoyed the previous 2 evenings filled with science and facts. We continue tonight where we talk about Till Death Do Us Part, where we have Alexander Rothkopf talking about dying particles in the Little Bang, Hege Ersdal about safer birth, and Frederic Bouder about risk. Our first speaker is Alexander Rothkopf from the University of Stavanger. He will talk about the dying particles in the Little Bang. He is an award-winning associate professor here at the university who obtained his PhD in physics at the University of Tokyo in Japan in 2011. After that, he worked at several different places as postdoctoral scientist, including the University of Bielefeld in Germany, the University of Bern in Switzerland, and the prestigious University of Heidelberg in Germany. There, in 2016, he became principal investigator and scientific manager of the Center of Excellence ISOQuant. And in 2018, Alexander moved to Stavanger, where we're happy to have him as an associate professor in physics. Please, Alexander.
Thank you, Mark. Hi everyone, my name is Alexander, and over the past 10 years I've been working to uncover some of the secrets of dying particles in the Little Bang. And I'm really excited to share with you tonight 3 facts from my research field. So let's start. Fact number 1, particles are everywhere. So this is really what got me fascinated with particle physics in the first place. And really, not only are we ourselves made up out of elementary particles, but the world around us is actually teeming with particles all the time. And to show you that this fact is actually true, I took a little trip last week. Check it out. Hi, we are here at the Science Factory Museum in Sandnes, Norway. It's a great place. You should check it out when you have time. The link is in the description below the video. So why are we here? We are here because there's an amazing machine on display at this museum, which is a cloud chamber. Cloud chambers were originally invented in 1911 by Charles Wilson, and they were used to study the highly energetic particles that come into Earth's atmosphere from supernovas far out in the universe. We call them cosmic rays. The modern version of cloud chambers were actually invented in 1936 by Alexander Langdorff, and it is this type of modern cloud chamber that is on display here at this museum. So what is a cloud chamber? A cloud chamber is an apparatus that has a hot part and a cold part. In the hot part, you evaporate alcohol into a really fine vapor that then enters the cold part of the machine that's at the bottom. So the temperature is so cold at the bottom that the alcohol vapor wants to almost condense, but it's tuned such that the alcohol vapor just doesn't yet condense. What then happens is that if an electrically charged particle plows through this vapor, it starts to kick the electrons of these alcohol molecules, and those kicks are just enough to make those molecules condense. And then what you will see is that there is a trail of droplets, a condensation trail forming along the path that this particle took. And if you look here, if you look down a bit, you will see that there's a lot of activity going on. Many different particles can be seen here. Most of the tracks that you will see are actually long, thin tracks, and these are produced by unstable particles called muons that are produced in our atmosphere. Fun fact, muons are actually the particles that gave us one of the most anticipated science reveals of the year 2021. And you can find a link to this topic also in the description. So there are these muon particles, and they're actually, sometimes you can see them die. And where can you see them die? Well, you can see some of these long tracks to make a kink and go over into another thin track. And this is where an unstable muon dies and decays into an electron and to neutrinos. Then you will see other types of tracks, thick and thin, thick and short tracks, for example, and these are coming from so-called alpha particles, which are essentially two protons and two neutrons smashed together. And what you see here is that particles are really all around us, and it's really fascinating to me that we live in this world that is filled with particles, and this is essentially why I want to understand particles. Isn't it amazing how we can make visible all these particles floating around us here with a cloud chamber? Well, in the 20th century, physicists really made progress by cataloging all the different species of particles that they could find out in nature and to better understand their properties. For example, how heavy is each of these particles? Now, in the 21st century, physicists are now trying to test out the limits of that knowledge. And how do we do that? Well, we can ask an athlete. How does an athlete test out his or her limits, for example, when it comes to endurance? Well, you go and do something extreme. You do something like training for an Ironman triathlon. And if you managed to finish an Ironman triathlon, you know that your endurance is up there and that you can take it on any other type of sports that requires endurance. And similarly, modern physics also has some sort of its own Ironman challenge, which is that we want to understand the physics and the properties of particles under the extremely high temperatures and the extremely high pressures that existed shortly after the Big Bang at the beginning of our universe 13.7 billion years ago. Because the idea is that if you know the physics there and if you know how particles behave in such an extreme situation, you surely understand how they behave anywhere else in the universe. But then, how can we investigate particles under such extreme conditions? And that brings me to the second fact I brought for you. Fact number 2 says, well, you can use particle colliders to create, or better, to recreate these extreme conditions that existed shortly after the Big Bang in what we call a little bang. And where does such a little bang happen? Well, one great place to do that is the Large Hadron Collider at the CERN laboratory in Switzerland. Here we are in Norway, and Norway is a proud member and actually a founding member of this international science laboratory CERN since its foundation in 1954. And there's quite some strong activity on CERN-related physics here in Norway, contributing to the research efforts at CERN itself. So what is the Large Hadron Collider? Well, foremost, it is a 27-kilometer long circular tunnel dug in underground close to Geneva, Switzerland. And inside this tunnel, you now have a particle accelerator complex that takes a bunch of electrically charged particles and accelerates them to almost the speed of light. You take one bunch of particles and you accelerate them clockwise, and you take another bunch of particles and you accelerate them counterclockwise, and then you tell the machine to collide those bunches of particles at some point, and you build an experiment and a detector around that point, and you measure what's happening in this collision. And understanding what happens in the collision is exactly what we should do. And so let me give you a concrete example. So things that people do collide at the Large Hadron Collider at CERN are, for example, the cores, the nuclei of heavy atoms such as lead. So if you take lead nuclei, lead cores, and you accelerate them clockwise, and another bunch of lead nuclei, and you accelerate them counterclockwise, you bring them to nearly the speed of light, and by doing so, you give them a lot of what we call kinetic energy. Kinetic energy is really what makes a car crash more and more deadly as the velocity of your car goes up. And so you have these nuclei with a lot of kinetic energy, and now you let them collide. And to understand what happens there, we have to go and ask our good old friend Albert Einstein, because Albert Einstein has a very important message for us. And I'm sure that many of you actually have seen this message before in his very famous formula E equals mc squared. And Albert Einstein's message is that energy and matter are essentially the same thing, and you can convert from one to the other. And that means you now have these nuclei, these projectiles in your accelerator with a lot of E, with a lot of energy, and if you collide them, you convert that energy into mass, into new particles. And that is exactly what happens. So you smash these two projectiles into each other, these nuclei of light atoms, and a wealth of new particles is created. And if you think simply about it, well, if you now have all these particles bouncing around, kicking each other, and if you think about what happens when you usually bounce against something else, there's friction and things heat up. So what we expect is that inside this collision, we estimate that there are temperatures of around 2 × 10⁻12 degrees Celsius. That's a number with 12 zeros. That's an unfathomably high temperature. And well, let's see whether we can find some other very hot place, maybe in the universe, that we can compare. And in our solar system, another very hot place is, for example, the corona of our sun, where we have around a few million degrees Celsius temperature. That's a number with 6 zeros, so still much, much colder than what we produce in such a little bang. Now I told you that this is an estimated temperature, and you may ask me, well, haven't you measured that temperature? And that brings us to fact number 3. And fact number 3 says you can use dying particles as a thermometer for the little bang. So what's the challenge? The challenge we have as physicists is that we cannot measure the temperature of such a little bang from the outside. Our system is too fast to watch, too hot to touch. So there doesn't exist any engineering material that could withstand such enormous temperatures to stick it in as a thermometer. And these little bangs happen on extremely short time scales, meaning they happen at around 10 to the minus 15 seconds. That's 0.14 zeros before some other numbers show up. That's enormously small time spans. And for example, there doesn't exist any type of laser that is fast enough to image such kind of a collision. So what to do? Well, what we try to do is to use the particles that are produced themselves as a thermometer. And that brings me to an idea that fascinated me already when I got into my PhD program, and that is that dying particles can become the sugar cubes of the little bang. And what do I mean by that? Well, think about a hot cup of tea, and then you put a sugar cube into that cup of tea. What you will find is that the sugar cube melts over time. The hotter the tea, the easier it is, the faster it happens that the sugar cube melts. So what's happening in there? Well, the sugar molecules are held together by a force, and that force is the electric force between the sugar molecules. Now, when you put the sugar cube into this hot tea, you have all these hot water molecules floating around. They're kicking the sugar molecules. They're making the sugar molecules go nuts. And what happens is that the force that's acting between the sugar molecules cannot keep them tightly together. And the hotter the tea, the more efficient the tea water molecules are in breaking this force apart and making the sugar molecules melt into your tea. So how does this idea help us for a little bang? Well, I told you that we create a lot of particles in this collision center. And sometimes, but just sometimes, it happens that some two elementary particles are produced very, very close to each other, and then they can stick together. And they stick together and they form what we call a bound state. So what's happening there? Well, these two elementary particles are held together, again, by a force. But this force is not the electric force of the sugar molecules, but it is actually a different type of force, and it's called the strong nuclear force. Well, as the name says, the strong nuclear force is much stronger than the electric force, so it can hold these particles together much more tightly. But also the strong nuclear force is not invincible. So if now our bound state sits in this really, really hot environment, it gets kicked by other particles. And if the environment is hot enough, it too can it can overcome the force that keeps those two elementary particles together, and they fly apart, they melt, and this bound state dies. So how can we use this as a thermometer? Well, if we know up to which temperature the strong force can keep those bound states, those two elementary particles circling each other without melting, without dying, well, then they will survive. And our friends at CERN can measure that these kind of double particles fly out of the collision region. And if they measure them, they know that the little bang they are observing is below what we call the melting temperature of this bound state. Conversely, if you carry out an experiment where you create a little bang that has no such bound states flying out of its collision center, well, it's a good guess that you reach a temperature that is higher than the melting temperature of these bound states. And so if we can map out all the different melting points of these bound states of elementary particles, we can really use that as a thermometer for the little bang. And that is what I'm doing here at the University of Stavanger. I'm designing algorithms and writing software programs to simulate the behavior of these elementary particles as they swirl around each other in a hot environment, and want to better understand when do they melt, when do these states die, and then try to communicate with my friends at the CERN laboratory together to figure out from their measured data and our simulations how hot the little bang was that they created. And with that, I'm at the end. I hope you enjoyed the 3 facts. Particles are everywhere. You can use particle colliders to create conditions that were very similar to those close to the Big Bang. And you can use dying particles, dying bound states, as a thermometer for the little bang. Thanks for watching.
Well, thank you, Alexander. That's truly fascinating about all these amazing little particles and recreating the little bang in CERN near Grenoble. So our next speaker is from dying to birth, and she's Hege Ersdal, who works at the University Hospital. Unfortunately, Hege cannot be here, but she made an amazing video for us to look at and to see the amazing work she does with her team. So she cannot answer questions, but please do stay and watch. Hege is the head of research for simulation and global health at the University Hospital Stavanger, and also a professor here in the university itself. She obtained a PhD in international health at the University of Oslo, and she's a trained anesthesiologist and the leader for the critical care and anesthesiology department in the hospital. Since 2009, she's the principal investigator of a large international team interested in labor and newborn resuscitation, and she's especially interested in the implementation of simulation-based learning to improve critical care. So please enjoy the video from Hege.
Thank you, Mark. My name is Hege and I am a medical doctor. For more than 10 years, I've been working to try to make birth safer all around the world. Because every year, around 150 million babies are born. Most of them actually look like this baby. It's healthy, screaming, breathing, and pink. Our research have found that about 85% of newborn babies, they will start breathing on their own just after birth, actually within seconds. But as much as 15 million babies every year will look more or less like this baby. It's floppy, unconscious, and bluish. It's not able to start breathing. They need help to start breathing. And most of them do that because of what we call asphyxia. Asphyxia means that they have received too little oxygen during the labor process. So they have too little oxygen in their blood. And then we call it asphyxia. Looking at that picture, it is a little bit difficult to really say whether that baby is dead or still alive. If it is still alive, it is in urgent need of help to start breathing. However, as many as 3 million babies are dead at birth, and we call them stillborn. And another 2 million babies, they will die just after birth every year because there is not anyone there that is skilled and with the proper equipment to help them to start breathing. Looking at all these devastating numbers, we actually believed that most of these deaths could be prevented by simple actions that could be done everywhere, better equipment, and better trained healthcare workers. So around 10 years ago, we started the Safer Births project. It is a research and innovation project to save newborn lives worldwide. And we, that is the University of Stavanger, the Stavanger University Hospital, together with Hadron Lutheran Hospital in rural Tanzania and Fetal Global Health, which have their main office here in Stavanger in Norway. We started by setting up a rather unique research infrastructure at this rural Hadron Hospital in Tanzania. And on this picture, you can see a baby that is just born by a cesarean section. The baby is floppy and bluish. However, in the corner of the picture, you can also see a research assistant that is observing everything that is going on with a stopwatch. She's taking the time on every event and every action that is taking place. This baby was asphyxiated. It was not dead. So the midwife moved the baby to the resuscitation table. And here you can see her squeezing the bag. She has a mask placed over the face of the baby, and when she pumps on the bag, she's squeezing air into the lungs of the baby, opening the lungs. On the picture, you can also see a green buckle that is placed over the stomach of the baby. And you can see a display, a monitor that is fixed, mounted on the wall just above the baby. Both these equipment were purposely made to help us to conduct good research. The photo is taken by a video camera that is actually recording all the resuscitation taking place. Putting together information from all these different devices, we have been able to study the process of the labor, the actions after birth, how to best resuscitate the baby, the responses of the baby, but also, very importantly, we have been able to study the actions taken by the healthcare workers. What do they manage to do well, and what are they struggle to do? Are they able to follow the guidelines? Because everything you had to do with a baby in this situation, you must do very, very quickly. And based on the knowledge, after watching the videos, for example, we understood how to perform better equipment for training and also design simulation scenarios that could really help the midwives to practice with a mannequin or a doll, as you see here in the picture. So this is a midwife at Hadron doing her weekly simulation training. Our research also told us that most of the babies that were born as stillbirths and many of the babies that were severely asphyxiated and without able to start breathing at birth. They were so because of lack of oxygen. And one way of monitoring these babies during the labor process is to follow the fetal heart rate. So that's why, together with Ersdal, we developed the Moyo fetal heart rate monitor, as you can see in this picture. With this device, the midwives could, in a much easier way, monitor the fetal heart rate of the baby during the birthing process. Moyo is also recording the fetal heart rate, so that gives us a measure to study everything that has happened during the labor afterwards. Nevertheless, some of the babies will be asphyxiated at birth. And now we are going to show you a simulation session, a scenario, about how the midwives can train to be better. And to do this, I will have some help from Siren, my colleague. For this demonstration, she will be my birth attendant, and I will deliver a baby. I hope you are able to watch that. I had to put on this simulator first. So this is Mama Natalie. It is easy to operate. It is easy to bring around. You just put it in a rucksack, and then you can walk to places where there are no roads. You don't need electricity. Hello, Siren.
Hi, how are you?
Oh, I'm in labor. I've been walking for so long to get to this hospital. Can you help me?
Yes, I can already see the head.
I have a contraction now.
Yes, you're doing so good. Very, very impressive.
Do you have all your equipment ready?
Yes, I have. I have something to dry the
I
baby.
think I actually have the urge to push now.
Yes,
Is that
I can
okay?
see the head. Go ahead. Very good. One more push. And there's the head out. Okay, the next contractions, you have another push and the body is out.
How is my baby doing?
It's looking a bit pale, so when you have another contraction, please push.
Oh, here it comes again.
Oh, and here's the baby. And it's looking very bluish and it's floppy, so I'm drying and stimulating the baby. It does not seem to be responding.
I can't hear any cry.
No, the baby's not responding. I'm very worried about this baby.
Does it have a pulse?
I'll put on the Neobit heart rate meter and see in the display that the pulse is very low. I need to separate this baby from the mother, so I cut the cord quickly, and then I rush the baby to the resuscitation table to resuscitate. When we get here, we dry the baby again and get rid of the cold towels and put on something dry to keep the baby warm. The pulse is still low, and we need to help the baby breathe because it's not breathing on its own. So we put the bag and the mask on, and we try to squeeze air into the lungs of the baby. And I'm struggling to get air in. I reposition the head, and now, yes, I can see the chest rising. But the baby is still blue, and it's not responding. I keep ventilating the baby, and now I can see the heart rate is picking up. The baby is doing better.
Oh, thank you.
The heart rate is coming up, and we're getting air into the lungs. I need to keep ventilating the baby until it's breathing on its own. Now it's moving a little bit. It's maybe starting to try and draw its first breath. But I continue to ventilate until it starts crying. Oh, fantastic. Yes, the baby's now doing good.
Very good, thank you.
You're welcome.
So, an excellent performance by a very, very clever birth attendant. So this is what Siren managed. She, in a way, transformed this very, very sick, depressed baby into a healthy breathing baby. And that is what we say, it's simple actions. It really doesn't need a lot of sophisticated equipment, but they do desperately need these first helps to breathe. So here you see a typical resuscitation table in Tanzania from Hadron Hospital. And you see the resuscitation table at Stavanger University Hospital. And the differences are striking when it comes to resources. However, the challenges for the healthcare workers and the pathophysiology of the babies are exactly the same in this low resource setting as we have here in Stavanger in a very, very high resource setting. So there are actually more similarities than differences. And this is why we decided, after approximately 10 years of studies in Tanzania, to bring much of the research back home here to Stavanger. And we actually brought some of the equipment as well. So if you look at the picture from Stavanger University Hospital, you actually see one of the ventilation monitors brought back home from Hadron. You can see a video camera up, and you can see the buckle, the Neobit buckle, that was green when we used it in Tanzania, and now it's black. So Siren, you are in charge of several studies at Stavanger University Hospital. Could you tell us a little bit about the two most important studies?
Yes, I will. So the Neobit heart rate meter study is a study where all newborns that are born at Stavanger University, they have the Neobit placed around their chest immediately after they're born. And within seconds, you have the heart rate displayed on the Neobit. And in this study, we want to see if knowing heart rate immediately after birth and throughout and resuscitation help us perform ventilation in newborns better. In the newborn timeline study, we have learned from Tanzania how critical the time from birth until receiving resuscitation is in newborns. So what we're doing is video recording with thermal cameras, deliveries in the operating theater and in the delivery room. And as you can see in this image, the baby has a temperature of 37 degrees Celsius, and it shows in a different color compared to the surroundings. So this will give us the exact time of birth. And we're also video recording the resuscitation. And from this timeline that we're developing, we hope to learn more of knowledge gaps, where we have to perform better, where we have to do simulation training.
And this is a collaboration between?
This is in collaboration with the University in Stavanger, with BIT Yoga and Lærdal Medical.
Very good.
So we are grateful to all the thousands of women that are participating in these studies here in Stavanger when they're giving birth. And we hope that together with these mothers and babies, that we can learn how to do births safer.
And that is actually also the ultimate goal of all the safer birth studies, to provide safer births on a global scale. And by combining all the new knowledge that we have been able to provide in the safer birth studies, together with all the innovative equipment, we have actually shown that it is possible to reduce the number of stillbirths by 25% and the number of newborns by 50%. So to all the superwomen giving birth and their newborns around the world, thank you.
Thank you.
Thank you, Hege. Well, that's just wow. I mean, absolute wow. Thank you for this. So we now have covered death and we've covered birth. Now we've got everything in between is associated with risk. So the next speaker is Professor Frederic Bouder from the University of Stavanger, who will talk about risk. Frederick obtained his Masters for Comparative Law at the Université Paris I at the Panthéon Sorbonne in 1992, and after that he moved to King's College in London, the UK, where he was a research associate. And in 2009 he became assistant professor at the University of Maastricht in the Netherlands. And since 2017 he is full professor here in Stavanger in risk management. Frederick, please.
Hello everyone. So it's a pleasure to see you all. I'm unfortunately in London, although I am in front of a pub. You could see that behind me, and I have a glass, so I stick to a pint of science. So today I will talk to you about risk. The concept of risk is something we are quite familiar with, especially in these days, the troubled days of COVID. And on the left-hand side, you can see just a symbol of that, us wearing masks to try not to catch the disease and hopefully not to suffer the consequences. So very often risk is seen as, something bad. It's the possibility or probability of harm, possibly even death. However, I wanted to give you a slightly different perspective on risk as well. And you can see that on the right-hand side. Here, some of you may have recognized already that this is about the story of Moses. And if you're not familiar with the story, it goes back to Pharaoh, who had decided that new Israelites who were born Hebrew boys would be killed. And Moses' mother decided to hide him and put him into a basket and launch him onto the river. Well, you could say that's a very dangerous action. It could have resulted in Moses dying and drowning, but that was also a way to save him. So in a way, risk taking can be very ambivalent. It can lead to something good. So now often when we think about risk, we think about probabilities and the odds. We think about rolling the dice. First of all, one way of looking at risk has often been to leave it to fate. Putting a child in God's hands, for example, is a way to look into risk. But of course, through the ages, and especially since the so-called Enlightenment and the rational era, we've been thinking about risk a bit differently in terms of not just possibility that something may happen, but also probability and how we could better estimate these probabilities. And that leads us to the notions of certainty. Well, the only very certain thing on earth is that we will all die, but also uncertainties. Will it happen? How might it happen? And I hear that there is an issue with my slides, but I will continue talking. Certainty versus therefore uncertainty, ambiguity, and complexity. Uncertainty could be about, let's say, will a substance cause cancer? And we don't have all the evidence, all the science about that. And we are wondering. And there is some discussions in science. So this is uncertainty. Ambiguity could be about different possible causes. For instance, there has been a lot of discussions about fertility, infertility, how, for instance, sperm counts in men would go down. And there have been various possible causes about that have been discussed. Is it about chemicals in the water? Is it about changing in lifestyles? Is it about other causes? So this is typically what ambiguity is about. And finally, complexity. A lot of risks involve a number of possible ripple effects, different causes and accumulative effects. And you could think about climate change, for instance. There's a lot of possible causes and consequences that all go into the various interactions that cause climate change. And therefore, when we think about the climate, we need to think in terms of the complexity of the risk. Another point about risk is, of course, that I've been talking here a lot already about probabilities. So a lot of these have been explored by, maths, statisticians. But we also conduct experiments to try to see what are the effects of, let's say, a specific chemical. What harm could it cause? And unfortunately, we've often used the poor mice as a way to see what is happening there. That is the entire branch of science called toxicology. So often, maths and mice are at the core of the risk discussion. Well, now I've been talking a lot about, what's happening around us in the world, but we have to also think about what's happening in our heads. And there, our brains can be both helpers and tricksters when it comes to risk. In a very illuminating book that was written about 10 years ago by Daniel Kahneman, he explored, from drawing on the work that he developed together with Amos Tversky, he developed a discussion about how our brains work. And the way our brain works is typically when we do analytical thinking, we have the slow part of our brain working, but we take a lot of decisions in a split second. These are fast decisions, and our brain is also fast. So our brain is both fast when it needs to act quickly and slow when it is more analytical. And what Kahneman talks about is also a lot of what we call mental shortcuts, as well as biases, that distortions that make our fast decisions distorted. So some examples here. One of the shortcuts could be the so-called anchoring heuristic. So when an event has taken place, we often think at that as a point of reference, and it has an impact on our future decisions about risks. For instance, during the tsunami in Japan, we had a nuclear incident, the Fukushima nuclear incident. Well, for many people now, this is an anchoring event. When they think about nuclear, they think about Fukushima and the incident linked to the tsunami. So they're really, really afraid of nuclear technology. Another typical mental shortcut is about availability of the information around us. This is the so-called availability heuristic. There, what happens is when we need to make a decision, we need to look at what's available for us to make our decision from. And this is, for example, if I catch a disease, well, I will think, okay, what do I think about this disease? What information do I have about it? And often, of course, it's not all the information. And by the way, our brain is not the perfect computer, so it has to discriminate. It can't take it all on. Finally, another mental shortcut I'd like to draw your attention to is the so-called hindsight heuristic. Well, hindsight bias, actually. There, the question is more, very often when we judge a situation based on our experience, and we judge on hindsight. So that's typically what many doctors would do when they see a patient and they have a first gut thought. Oh, well, that's a patient. Well, I've seen these symptoms before, and that must be this condition. Well, sometimes they get it wrong. So that's the hindsight bias. Of course, there are more of these shortcuts and biases, but I thought I would just stick to a few because I don't have a lot of time. Another aspect when we think about risk that is very important to consider is that our perceptions are also driven by a number of factors. When we think about risk as something natural, for instance, we are much less worried than when we think about it as something technological. And here I could take some comparative examples on both sides of the Atlantic of how people have been seeing the genetically modified organisms, so-called GMO food. Well, typically when this technology was first developed in the US, people were seeing it mostly as a natural thing. The next phase of human selection, we had been selecting crops for millennia, and now that's the next phase. Well, in Europe, when it was introduced, it was very much seen as a technology, kind of Frankenstein food, and therefore framed very negatively. And the perceptions were affected by that, much more positive in the US than in Europe. Another driver of perception is whether we feel something is voluntary or involuntary. When I take a voluntary risk, when I decide, let's say, to use my mobile phone voluntarily, I'm much less worried about it compared to when I am next to a pole, a mast, which emits waves to make the network of mobile phone function, mobile phone masts, then I'm more worried about it because it's not voluntary. I haven't decided to be there. I haven't decided to use the mast. Same with familiar and unfamiliar risk. When a situation is familiar, we tend to take more risk. And that an example is, for instance, when we drive on a familiar road every day, and we tend to be more reckless than when it's a new road and we haven't been there. And sometimes bad stuff happens there. Finally, when we feel we're in control, we are less worried than when we're not in control. And there's a typical example. If I stick to an example around cars, when we are behind the wheel of a car in control, we feel more comfortable than when we are next to the driver, or even worse, when we're sitting in a plane. This has very little to do with the probabilities that we discussed earlier. Whether it's a high or low probability doesn't make much of an impact. And often we overestimate small risks because they fall into these dreaded categories compared to other risks which would be more likely to happen, but we are less worried about. Before we part, before I shut up and leave it to the questions, I would like to highlight that in order to deal with risk in a less frightful way, in order not to be too afraid by risk, and to also make decisions that will save lives, that will help us, we need first better science. But when I say better science, it's not just better science in labs. It's not just also building better probabilities to understand uncertainties, ambiguities, and complexity better. This is very important. But on top of that, we also need science to understand perception, science to understand communication, so that we are engaging better and we understand that what we perceive and what we choose is not exactly what is always more likely or less likely. So this is a combination of both that is important. And after all, what we need also is as a society to make decisions. And in order to do so, we also need to be able to conduct some sound exchanges of communication between the key players in society. And what we need to try to achieve is not always consensus, because it's not always possible, but at least what Baruch Fischer, one of the key risk guy or risk professor in this world, has called better disagreements. We need to agree on the procedure. We need to agree on what we disagree in order to move forward. Thank you so much. I think it's time now for the discussions. Thank you.
Thank you, Frederick, for this presentation and all the unknown aspect of risk for us. Thank you for Frederick, Alexander, and Hege for these amazing presentations. We now just break for a few minutes to get ready, and please stay tuned because we start answering your questions. Thank you, and see you in a few minutes. Go.
Hello.
Hello and welcome back at Pint of Science Stavanger in Norway, where we now have time to talk to our speakers, Alexander and Frederick, who are here to join us. Unfortunately, as I said, Hege could not be here, so she sent us a pre-recorded video. But first of all, thank you both for all three of you actually for your nice presentations for our audience and to celebrate our understanding of life around us. So I got a few questions from the audience. Unhee Cho asks, interesting full of particles around us in the cloud chamber. I mean, it's truly amazing that we can't see these things and they're shooting straight through our bodies.
Through us all the time, yes.
So do you have a favorite particle?
Well, yeah, there's a lot of particles out there, and there are many cool particles actually. For my work, I really fell in love with these bound states that I talked about out of two elementary particles.
Yeah.
They are called quarkonium because they are made up out of a quark and an antiquark. And I've spent the last 10 years with these particles, so I'm really into them. If I had to pick one other particle outside of what I'm working on, I would say I would go for the muon, which is the heavy cousin of the electron, because you can do pretty cool things with muons. Muons are created usually in the atmosphere when a cosmic ray hits air molecules. And then you get this stream of muons essentially from the horizon everywhere you stand on Earth. And what you can do is you can put a particle detector for muons in front of a volcano, for example, and you can then record the image that you get as the muons pass through the volcano.
Okay.
And you can get like an X-ray image of an active volcano through muons. So Mother Nature gives us a natural source of muons in the atmosphere. They penetrate matter easily. You put in a detector and you can image volcanoes. They have used it to image pyramids. Pretty amazing, these muons.
And you said so they made when they hit the atmosphere. So muons don't exist in outer space?
So there might be muons flying out of celestial objects, but they have a very short lifetime, 2.2 microseconds, I think. And that means they will decay into an electron pretty quickly. So they should be produced pretty close to you if you want to observe them. So our atmosphere still works. They are fast, so they make it.
Okay, cool. And another question for you from Eva Pirihova. How do you make these particles, like these lead nuclei dimensions? So you can't buy them in a shop, I guess.
Well, part is actually of buying part of this. So at CERN, what they do is they actually buy pure lead 208. So usually lead in nature comes in 4 different so-called isotopes, so slightly different composition of the protons and neutrons that make up this nucleus. But then you would have to separate those 4. So at CERN, they actually buy purified lead 208. Then, well, you have a piece of lead that you cannot put in your accelerator. But then what you have to do is you have to heat it up. You evaporate it, but then you just have lead vapor. The next thing is you need to ionize these. So you have to get rid of the electrons of that lead atom, and then you have the highly charged nucleus left, and that you throw into a set of accelerators before you bring it into this Large Hadron Collider ring.
Okay, wow.
Yeah.
Okay, a question for Frederick. About what is your view on altruism?
What is my thinking about altruism?
For the greater good.
So I think altruism plays actually a big role in decision making. In the risk field, we've been very interested in that, for example, in relation to vaccines. It has been seen that altruism is one of the key drivers of people deciding to give the vaccine to their children or even taking the vaccine themselves. I'm not just talking here about the recent discussions about the COVID vaccine. Something has been studied for over 30 years. It's very interesting that people think, okay, my child is healthy. My child could experience some side effects from a vaccine. Of course, we hope that, the government, the regulator, as we call them, have made it all, under control, have kept it under control, but we can never exclude that something wrong happens. But we've seen that in, rationalizing why people still decide to say, well, there might be a very, very small chance something goes wrong, but I still want to take the vaccine, or I think my child should have the vaccine. One element that plays a role is also altruism. So I'll do that also for my child and for the children around my child. So that's a very, among different ways, among different aspects, it's one that plays a role, a factor that plays a role in people's decisions about risk.
Sure, thanks. Yeah, so I forgot to say there's a question. That was the question from Marion Sproker. Another question for you, Frederick, from Thibault. What is your opinion about the expression "blessed are the ignorance"? I mean, is there a risk of knowing too much when you want to?
So, as somebody who likes science, I don't think there is ever too much information, but the question and too much science. But the question is, how do you make a distinction? And there has been a long, discussion in the field of risk analysis about what we call risk assessment and risk management. So risk assessment is really, gathering the information and trying to make sense about the risk. But then there is a point where somebody needs to come and make a decision, because risk at the end of the day is about decisions. And this articulation between mustering as much science as possible, updating the science, making sense of the science and the latest consensus, because science evolves over time, and then having a decision and somebody, a risk manager, needs to manage, is a very important distinction. So I don't think there can be too much science. It's always good to have more science, but at some point you need to make decisions and look at the evidence, and sometimes have a hierarchy of, how you put things, what do you put higher, and you need to explicit that.
Sure, and then maybe also regarding the current situation where people are worried about vaccines and the corona and the epidemic in general, could managing information flow also be linked
totally
to risk
true.
then?
And that is why it's very important to have a good quality discussion, and to have to let various viewpoints being expressed, and manage that discussion in a way that builds trust, doesn't destroy trust in the discussion. And I recognize it's not very easy at the moment. It's not an easy task, but it's very important to listen to concerns, for instance, listen to people's concerns and address those concerns in a two-way. We like in the risk of in the field of risk talk about two-way communication channels. It's not just top down. It's not just telling people it's all fine. It's about two-way communication channels that could address worries and questions.
Sure. Yeah. No. That sounds like very, very important nowadays to allay people's fears by honest discussion of facts, I guess. So back to Alexander for a physics question. Here's Dan asks, where is all the antimatter?
Okay, that is a very good question. And we haven't yet figured out where all that antimatter went. But I think we know where to look. Let's say it like this. And I should say the cosmology group here at UAS, so my colleagues that work on cosmology all the time, are the experts to ask. So let me try a go at it. So essentially what you're asking is, why is more of the stuff that we are made out of, protons and neutrons, for example, are there, why there are not antiprotons and antineutrons around? And the category of particles that protons and neutrons fall into are called baryons. And the process of creating more baryons than antibaryons at the beginning of the universe, it's called baryogenesis. And so people have thought for many decades now about what needs to happen that at the beginning of the universe somehow more baryons than antibaryons survive. And there are three famous criteria called the Zakharov criteria that tell us what needs to happen. The first thing is you need some kind of physics process, and that's the easy, so to say, that's the straightforward idea, that produce more baryons than antibaryons. Okay, well, duh. But then you also need some additional physics processes that make sure that this imbalance that you create through this baryon number violating process, that they don't get washed out through other processes. So what Zakharov understood was that you need processes that break what is called CP invariance. So it's another type of thing that usually physics looks the same whether you look at a particle or an antiparticle, except for the charge. And so you need processes that work differently for particles and antiparticles. And for example, there's a class of particles called kaons that interact via the so-called weak interaction. And there you have, people have found processes that actually violate this CP symmetry. But it's not enough. Somehow that what they found is not enough to explain the imbalance that we see today. So that's one part of the solution. And the third Zakharov criterion is that the early universe may not be in thermal equilibrium, as he says. So if you put your bathtub full of hot water that is all at the same temperature, for a physicist that's a very boring system. If you were to now put don't do that at home, if you put in a heater coil at the one end of your bathtub where it becomes hotter, then temperature changes and things will move. And so for more baryons to end up in our universe than antibaryons, you also need these kind of imbalances. And so we know where to look. Baryon violating processes, CP violating processes, and somehow things need to be out of equilibrium. There needs to be change happening rapidly at the early universe, but we haven't yet found where all of that antimatter really is.
So you mentioned a lot of particles, yeah? Baryons, kaons.
Yes, kaons, yes.
Kaons. So Marion asked, are there still particles to be discovered?
Well, a lot of my colleagues do think that there is a wealth of particles out there that needs to be discovered. And we have somehow an idea that the current understanding of physics is not complete. So at the moment, what we have is called the Standard Model of Particle Physics. It describes almost all of the particles we know, and well, it describes all the particles we've observed, but it makes slightly different predictions for some of the properties of these particles. So for example, there's a class of particles called neutrinos, and neutrinos in the Standard Model should have no mass. But if you measure neutrinos in the lab, you find they have a tiny, tiny, weeny mass. And that means that the Standard Model is not making 100% fully correct prediction for all the particles we know. So there's something still missing, and there could be a particle lurking somewhere in the shadows that is responsible for making these neutrinos a bit heavy.
Maybe this also relates to a question from Thibaut. How close are your simulations versus the experiment? Because that's probably how you know there might be something missing, I guess.
Well, I myself, I'm not a particle hunter, so to say. I'm not hunting for new particles. I'm really staying with particles we have known for many decades now. I'm interested in these quarkonium particles. They are made out of a quark and antiquark. And quarks are known or are part of
how we describe nature since the 70s, 80s. So what the challenge for my research is, well, I want to describe what happens in such kind of collisions with as few as possible assumptions. So I just want to start from the basic equations that we believe describe quarks and the force between them. And I want to make as few assumptions before making a prediction for the melting of these particles. And so far, I have not yet fully managed to explain experiment because I still don't yet know how to write the algorithm that allows me to simulate these particles in a realistic environment. Usually I can only simulate them up to now in a somewhat idealized environment. And again, it's the bathtub that's very boring. If I put my particle in the bathtub, that works. If I start to stir the bathtub or heat the bathtub, well, then I'm not yet there. So that's the challenge. We are close, but we're not yet there.
No. So more work to do.
Definitely more work to do.
Okay, thanks. A question for Frederick from Sanya, I hope you pronounce the surname correctly, Mrzik. So what were the most surprising risk perceptions in the case of COVID-19 pandemic?
It's a really good question. It depends surprising on what level. I think it was very interesting to see a shift in some perceptions, and from at the very beginning, it's just like the flu to maybe sometime overreactions. We understand that, for example, very high proportions of people who are very unlikely to die, and that's very good, think now that they might be at risk of dying. So what is important there is to understand, when we talk about perception of a disease like COVID, is how much has there been attenuation or amplification from the media and from the various discussions in society. And probably it's been one of the most discussed issue in society. So this is where, the field of risk communication can become very interesting, because you can understand some of the drivers of perception. You can understand, why it's not so surprising if it's a novelty, if it's perceived as a new disease, that there will be some heightened perception. On the other hand, if people anchor it with previous experiences of the cold or the flu, then maybe that will play actually the other way around. And so understand these dynamics into working around, how to best communicate the risks, that like some populations are more at risk, less at risk. Some behaviors can lower the risk or increase the risk. And then you can work around, trying to bring more science into the discussion.
Yes, I guess the pandemic is, for people like you, is an interesting field lab. I mean, there must be such amazing data suddenly appearing from everywhere, different layers of population.
Yeah.
Governments all handled it differently.
Well,
so I guess
we're very proud that we have a project called PanFight that's ongoing, and one of the actually the leader is our university, and it's financed by the Norwegian Research Foundation, and this project has partners across Europe, in Sweden, the UK, Germany, and Switzerland, and we are precisely looking into these various factors, both the perception, the communication, but also the institutional response, and we are looking into trying to again improve the response to pandemics in the future, based on the risk field. So that's indeed has led already to some very tangible development, and we are hoping that it will help to deal better with future pandemics as well in Norway and beyond.
Of course, very good. And another question for you, Frederick. Early Joe asked, are the media and
Yes,
social
I think they
media
are both.
helpers or hindrance in your case?
One of the famous risk professors based in London, I did my PhD with him, called Ragnar Lofstedt, actually worked about now over 10 years, 15 years ago maybe, with the BBC in the UK to try to work together with journalists to develop science reporting guidelines that they could apply to themselves, so co-developed between science and journalists, so that it helps them to better report science. And that tells already, the problem that we've been seeing, that it's critical. They play a critical role, the media as well as social media, both the conventional media and the social media. They play a critical role in the discussions that take place in society, in informing people, in discussing. But at the same time, they can sometimes, misrepresent what is happening. And of course, the answer to misrepresentation from a risk communication perspective is not just to say, well, they have to shut down. But what our view is more like, okay, we have to help build this capacity to do a better job. And again, at the very early stages of the pandemic, what we saw is a lot of attenuation, and then we saw a lot of amplification, and it's important to keep that in mind. So yes, they are both useful and a challenge. So I see it more as a challenge rather than, a negative.
Sure, but I guess the unpredictability of what comes out of any of these channels is probably...
Yes, and I think what is important is, again, to always keep track of, what's going on, what are the areas where people are worried, what are the perceptions out there, what are the issues being discussed, and how you can inject more science into this. Again, understanding that science also evolves, that science is something that evolves in relation to new knowledge that is constantly produced. But it is important to understand that interaction and try to mediate. In that sense, what we call neutral third parties, people who are don't have a vested interest in any discussion. Now I'm going beyond this particular discussion on COVID, but more generally can really play a role in mediating between the various branches of science and government and industry. So people like us, like scientists, can really help to be at the core of the discussion.
Yeah. So maybe a question to both of you as a final question. So I remember a few months, or maybe my brain is a bit foggy, when the physicists at CERN wanted to recreate the Big Bang, or maybe the Little Bang. I saw parts in the newspapers, I think it was the British press, where people said that scientists want to recreate the Big Bang and could lead to the end of the Earth, of the universe as we know. And so, so I guess Alexander could answer that, if the risk was genuine on it or not. Frederick can maybe just also, would you like to sign off on an experiment what actually might lead to the total end of the universe? So it's maybe on a lighter note, this question, but I guess if you want to recreate things which result in 200 billion degrees centigrade conditions, then the risk management is pretty severe, I guess.
Okay, I take the challenge. Yes. So the first thing we should make clear to ourselves: we are puny humans. The biggest machines we build are tiny in comparison to the accelerators that the universe has in store out there. We heard about black holes from Alex Nielsen on the first day. These massive astronomical objects accelerate particles to energies that are so high that we could never accelerate them here on Earth. And these kind of particles are hitting us all the time, coming from the depth of the universe. And one of the arguments why the particle experiments we are doing here are safe is that, well, much higher energetic particles are hitting us all the time, and we're still here. So the risk associated by those surely very energetic but compared to the universe, really not very energetic particle collisions, is negligible. And before I hand over to Frederick, there's actually a court case described in the, I think in the California Law Journal, about an injunction against the Large Hadron Collider, where people actually asked a judge to decide whether to file an injunction against the LHC, because, and the jurisdiction was applicable because the US is a project partner of the LHC. Mm-hmm. And so then there was this, essentially this poor judge who of course could not understand the physics behind the particle collisions, but he now had to figure out whether there is a risk by, for example, finding out how consistent are physicists among themselves in the evaluation of risk for this collider. And finally, this case was dismissed, but it showed that there are ways how to judge physicists' statements, even if you are not.
So first of all, of course, nobody wants the end of the world, but and the whole purpose of the risk science is to keep things in balance. You know, not taking reckless risks. But I understand from Alexander, who is a very serious guy, that it was not the case there. So not taking reckless risks and not at the same time trying to eliminate every risk, because you know, we need, and I hope that's one of the message I gave, we need some risk, but not being reckless. The second comments I would make in relation to your question is actually, there is also a case for better science reporting in the media. And that's something we've been discussing for a long time, that there used to be a lot of scientifically trained journalists, you know, science reporters who had a scientific background. And they would have been more helpful probably in reporting what Alexander and colleagues are doing. And unfortunately, increasingly, we have too many journalists who are simply moving from one job to the next without any scientific training. And that creates sometimes a challenge in understanding what's going on and maybe reporting things the way you describe. So I am a big advocate also of, you know, recreating more science training for journalists and linking the science to journalism in a stronger way, so that you know, we get a better picture and maybe less lawsuits as well.
Good. Yeah. Sounds like a good plan.
Interesting.
Thank you.
Yes.
Thanks. Okay. I thank you. Thank you both, and Hege, who is not here, for your amazing presentations and opening up your research fields to the.
Thanks for having us.
Yeah. No, more than a pleasure. And I hope we see you next year again at Pint of Science Norway in Stavanger. And as you see, with the last 3 days, we here at the University of Stavanger are contributing to the knowledge for humanity, and we are here to challenge the well-known and explore the unknown. And thank you for that, and good evening from Stavanger, Norway.
And let me say one last word. Also a big thank you to our host today, Mark van der Giesen. He's a professor in biochemistry here at UAS. Thanks for guiding us through this evening. And a big thank you also to Daniel Alvestad. You have to pan a bit on your mobile phone to see him coming into the room. Daniel is a PhD student in my group, and if you want to hear more about cool quantum simulations and stuff, you will have to ask him to present the next time at the Pint of Science. Thanks, Daniel, for manning the control room.
Thank you.
Thanks.
And with that, we leave you from Stavanger, Norway, and hope to see you next year. Bye-bye, everyone.
Bye-bye.
Oh, it's the Christmas party.